everybody kind of did different stuff last year. It was kind of a wacko year, as we know. So you may or may not have talked about some of this stuff, but that's okay. This is kind of like as we're leaving pre-calc, if we're going into an algebra-based class, which a calculus class would be an algebra-based class, these are like the basic things you should know some stuff about. Okay. All right. So 3 basic functions up here in the front. If we look at this function, just a plain old horizontal line function, a horizontal line function is just y equals. In this case, it would be y equals 1 because it goes through the point 0, 1. But basically, y equals any number is just a horizontal line. And we should know that for a graph. What's the y equals 3, y equals 7, y equals 106, y equals negative 25 and 3/4, whatever. Those are all just horizontal lines. Okay. Now, when you have a horizontal line, you got a pretty boring domain. We love it when the domain is nothing exciting. No holes, no vertical asymptotes, none of that nonsense that happens in rational functions. Lots of algebraic functions have negative infinity to infinity for their domain. And in this case, my range is just a single number. And so oftentimes if our range or our domain is a single number, we use the braces to represent it's just that set of that one number. I always make those weird, so just 1. If the equation had been y equals 3, then, that would be up here in red, and the range would have just been 3. Now, so for each of these, we're just writing an equation, the generic equation. We're talking about the domain and range, and then we're going to talk about whether it's considered an even function, an odd function, or neither. Those are your 3 options. Evenness versus oddness versus neitherness has nothing to do with exponents or any of that. Like even degree, odd degree, we know means certain things, but even and odd behavior is something different. Even has to do with, and odd has to do with symmetry. So a function that has symmetry along the y-axis, where the y-axis essentially acts like a mirror. You could fold this, if you could pick up your paper, well, you could. If we pick this up and fold it over along the y-axis, if both pieces of the graph would meet up, that's considered an even function. So every horizontal line that we talk about automatically is an even function because we have that y-axis symmetry. The y-axis acts as a mirror. I'm going to make that little note here. We could fold across the y-axis, and the 2 sides of the graph would meet up perfectly. Okay. Just like when you would, I don't know, I always just think about when we make hearts in elementary, you fold the paper and then so the fold makes half the heart. All right. So that's an even function. And so if we skip over here just for a second, this guy, what's the name of that V-shaped guy? Y equals, do we know him? Yeah, that's the absolute value. That's the absolute value function. He's another even function, okay? Absolute values are also, in their basic form, are even functions. Now, any function, we can do a transformation on it, and it might then no longer be even or odd or whatever. If we move an even function over to the left or to the right, it's not even anymore. But an absolute value in its natural form is even. Domain, we love absolute values because they're easy. How would you write the range? think I heard it. Range value starts at 0. And we're going to include 0 because it actually hit 0. And then anything above, oops, I don't know why I'm writing the infinity as my comma. So 0 to infinity is absolute values domain range. If you're in a calculus class and you talk about doing things with different functions, sometimes it's important to know what the domain or the range is of the function. So knowing kind of what an absolute value looks like helps you visualize certain things that would help you understand things about domains and ranges. Also, in calculus, it's super important if there's a sharp pointy part, and absolute values have a sharp pointy part, so it's good to know that, where horizontal lines don't. Middle guy, just a regular line. This is kind of the basis of every other regular line that we graph. A regular y equals mx plus b line, and I'm going to kind of write that up here, is built out of this line. This line specifically is the line y equals x. Okay, 1, 1, 2, 2, 3, 3 are all points on the line, and same thing into the negatives, -1, -1, -2, -2, -3, -3. Domain, like anything linear, as long as you don't have any holes or anything, all real numbers, negative infinity to infinity. Range is the same thing. But this line, specifically the y equals x line, is an odd function. Now, the geometry way to describe an odd function is that it has 180-degree rotational symmetry around the origin. I hate geometry. When I think about odd, I think about, here's my thought. If I folded it twice, it would match up. Essentially, that's what rotational symmetry happens. If I took this and I folded this over, this guy would be over here, and then this, if I folded it down, the two pieces would match up. So you kind of have something here and something here, and if you fold it over and down, they would match up. That's rotational symmetry. I have a hard time turning my head to think about rotation. I have a hard time visualizing that, but I can visualize kind of folding and folding. At worst case scenario, my paper, I'm like, oh, look, if I folded and folded, yeah, this piece, this would go over here, and then this would go, this piece maps to here and maps to here. That's an odd function. I always kind of remembered that because odd functions, you kind of look for the symmetry over the origin, over 0, 0. And that kind of helps me remember, hi. Thanks. Okay. So I'm going to write origin symmetry, which is kind of a weird thing to say, but I'm going to write the double fold thing. So, like I said, here, if we folded that over that way, we would get this guy, and then if we folded that, those two pieces would look. Okay. Can we say that again? Yeah, absolutely. So the double fold is just how I think about it. That's not an official geometry description, but this is Willow Rock making sense of geometry for herself. But fold it over, fold it down, two pieces match up. That thing's an odd function. It's got the origin symmetry. Okay. These two you should recognize, I'm hoping, based from our polynomial unit. So if you want, take a second, go ahead and give me, if you can, the equations for these two guys. If you can't do that, then at least what would you say? Ooh, and they have names. What would you say for the domain? What would you say for the range? And what would you say for even versus odd? All right, make sure I got everybody that came in. That was my only person that came in yet. Okay. I will probably stop the video after this page and then kind of do it in chunks, because otherwise it's too long. Okay. Yep, our friend, everybody's friend, the parabola. This is the generic parabola. If we're talking about other parabolas, we use ax squared plus bx plus c, and then sometimes have that written in some kind of graphing form. So different quadratics. This is our generic quadratic. I'm going to write quadratic. I'm also going to write the word parabola or parabola. Just have a student tell me. It's a parabola. Yeah, okay. What's my domain? Yep. So domain, even though it looks kind of constricted, you're like, what about here? It gets wider and wider and wider. It does it very slowly, but it does happen. Another way for me to think, when I used to think about domains as a student, I'd be like, well, what am I allowed to plug in for x? Is there anything I can't plug in for x because there's some weird rule, like with square roots and denominators? Something like an x squared, I can plug in any number I want for x. So yeah, domain is negative infinity to infinity. Any number could be x for an x squared function. But you're only going to get non-negative numbers back. You're not going to get negatives when you square. You're either going to get a 0 or you're going to get a positive. So my range, my outputs are 0 to infinity. And is this guy even, odd, or neither? He is even, yes. Mr. Parabola. Yes, it could be Miss Parabola. Miss Parabola is even. The parabola is even. And then cubic cube. This is a cubic function. It doesn't have another cool name. It's the same shape as the tangent. Like the tangent curve is sort of shaped like an x cube. They're similarly shaped, but it doesn't have another cool name like the quadratic does, where it's also called a parabola. It's just a cube function, cubic function. Domain and range. X can be anything, and you're going to get all kinds of y's back. You'll get positive y's when x is positive. You'll get negative y's when x is negative. You'll get 0 when x is 0. All different kinds of y's. Even, odd, or neither. This is odd. So once again, if I could think about this, if I flipped him over here, it would be here. And then if I could flip that, I don't think I can flip it. Yeah, I can't flip it. So Can't flip it, but I can imagine it. So flip this over here, it would be there, and then if I flip that down, it would match up like that. So that's my odd. So a neither, we're going to get to some neithers next. Okay, so neithers basically just don't have good symmetry. It's just, these are the only, yeah, or, okay, like, yeah. All right, how we going? So some of the things you'll do, one of the things you'll do on the test coming up on the 27th is I may give you a graph. I will give you a graph and I'll say, hey, is this an even function or an odd function or neither? It's more about knowing visually what you're looking at. So even if it's not a function that has a special name, if it's just a function graph that's like a random graph, what kind of symmetry do you see, if any? And if you see that y-axis symmetry, then we go with even. If we see the origin, rotation, magic symmetry, it's odd. Otherwise, it's neither. And the middle guy right here on my next page is a perfect example of a neither. A lot of the other functions also, once you move them around, that graph, their graphs will turn into neithers as well. Okay. So, this graph, let's talk about him in the middle. He's definitely a neither in terms of even versus odd. He doesn't have y-axis symmetry. He doesn't have the rotation symmetry. It's just that one little piece. Does anybody know what that one is? Just does that one little branch? Right. That's square root of x. Sometimes we do plus or minus square root of x, and that means we get this kind of piece down here, but that's not really a function once you start doing that. Okay. So if we want to talk about just the function form of this, we're talking about y equals positive root x, and we get something like this. Domain, just non-negatives for x. We can't put negative numbers in for x. So 0 to infinity. We're not going to get any negative numbers out for y. When we start to take square roots of negatives, that gets into the concept of imaginary numbers, which are important for different types of mathematics. For the things we study in calculus, actually, we don't talk about things that are imaginary. Okay? Not in beginning calculus. So this is our square root. And next door to him, to the right, is the cube root. Now, in calculus, when we're talking about these two functions, a lot of the time we are going to use their exponent names instead of using a root. So we'll need to know that the square root of x is the same as x to the 1/2. And that the cube root of x is x to the 1/3. I know that's something you spent time on in Algebra 2, translating between, things written under radicals, different, I think it's like the root and the index. Okay, so a square root is a 1/2, a cube root is a 1/3. Knowing that, like I said, there's certain things we do in calculus that it's important that it's easier to do, or it's important to do it with that form of the equation. Cube root. Boring, boring, domain and range. Nothing fun and exciting. And even, odd, or neither. It's an odd. Yep, that's an odd. Like I said, it's kind of like, this is another way to think about it. 1, 1, negative 1, negative 1. An opposite x gives an opposite y when you're talking about an odd function. 1 gives you 1, negative 1 gives you negative 1. The next point on this cube root would be like 8, 2. And then there would be a point out here, negative 8, negative 2. Opposite x's give opposite y's. So first quadrant points and third quadrant points kind of work together. Or if you had second quadrant and fourth quadrant points. This last one, this is the basis of all of our rational functions. So all that stuff we did in Unit 2 with a numerator over a denominator, they're all built around this guy. The generic form is 1 over x. That's sort of the generic rational function. And then every other rational function is some variation of that. Rational functions have oftentimes horizontal and they have horizontal asymptotes and they have vertical asymptotes. So that's what you're seeing here. We spent a lot of time graphing like really complicated rational functions and talking about all the details of the holes and the asymptotes and how to draw in the curves. For most rational functions, at least the basic rational function, we just need to know a couple basic things. First of all, we've got a horizontal asymptote along the x-axis. We've got a vertical asymptote along the y-axis. And so what that does is it splits our domain at 0 and it splits our range at 0. So there's a piece of the function that goes from negative to infinity to 0x and negative infinity to 0y. That's kind of this bottom branch. A lot of times we call these branches. And then this branch up in the first quadrant is the 0 to infinity x with 0 to infinity y's. Positive x's and positive y's. And negative x's giving us negative y's. So are we talking even, odd, or neither? Opposite quadrants across the origin. Yep, that's an odd. Okay. Let me see what this is. Oops. Hold on, I'm just seeing if I'm getting any drama information about, oops.